Hi, everybody. Today we're going to kind of move into our second category of problems, and we're going to examine some exponential application problems. And so what you see on the top of your screen is just an initial breakdown of what an exponential function is, how it's defined, and maybe some situations that are going to cause us to be able to recognize that something is exponential. Keep in mind that our kind of mission for you, our goal for you in this, is not to be able to memorize how to deal with an exponential problem and then spend some separate time memorizing how to deal with a quadratic problem. And then that the purpose of doing all of these applications in one time frame is for us to be able to bounce back and forth between types of applications. Now you're fluid with stuff, which means you're more capable, more resilient. So I want to make sure that we're not starting today going, okay, this is a separate type of problem, and I now am only going to be responsible for this type of problem. We have to have the ability to be able to take what we worked on previously, quadratic problems, and be able to recognize when something is exponential. So what you see in green then is we can understand that something is exponential because of repeated multiplication. And you see at the top of that screen the use of the word population. Now, I just want to make sure that we're good, that when I underline population, I don't necessarily mean people. I just mean a group of something. That something could be dollars. It doesn't have to be people. So when we say population, we're talking about a group of something that is going to change by multiplication. In purple, below that, you'll see some quick examples. If we heard an application where the population tripled, or something was increasing or decreasing by a percentage, then we're changing through multiplication, and therefore we have an exponential function. So let's then examine this big formula-looking thing that lies in the middle of the screen. Now, I want to be clear that I don't talk about this as a formula. Really, it's a relationship of something. And it's a relationship that's built that's pretty common. However, I've kind of come to terms with what each one of those letters or variables represents and what spaces they hold. So, briefly, what we end up having is this big formula or relationship that says A equals P times G to the T over P. And I want to kind of break down the components of that. So the first thing that you'll see on the left side in blue is that's our accumulated amount. And one of the mistakes that people make is they see the word or hear the word accumulated, and we think about accumulating something as building it up. We have to be clear that we could also be building up losses. So over time, something could be becoming less and less and less. That really all the accumulated amount represents is the changed amount. You'll see in green, we have our big P, and that represents our initial population. And we're all good that initial is another way to say starting population. Now you see the multiply. So there's one form of multiply in the relationship. You'll also then see in red the big G. And what that G represents is our growth. And so you would know what the value of G would represent if you could answer the question, how is the population changing? Now you look up in the exponent, and there's your second form of multiply. We have a power at the end of that relationship. And because it's a power, there's our repeated multiplication. Up in the exponent, you have a fraction. On the top of that, you have in yellow your t, that's your elapsed time. And it doesn't always have to be time, but it's the number of repeated changes. On the bottom of that exponent, you have in p, that's our little p. And I understand that when we go through and we write things, a big P and a little p can only be seen to be different if they're put side by side or if there was like lines on the page. but I couldn't think of a better letter to put in there. Sometimes you would actually see it as like PD to represent period. So we put a little p in there. What the period is if you could answer the question, how long does it take to G? Now, I know that sounds like a weird question, but once we know how the population is changing with G, then what the period represents is how long does it take to do that. That formula or relationship is true for every exponential growth or decay problem, an application problem. And so if you like using formulas or relationships, that can be something that is very general for you, which makes it very useful and pretty easy to use. So what I want to do for the rest of this video is to work our way through and see how that relationship applies, how we can use it, and then to look for some of the little quirks or considerations that are going to pop up that make sure that we become very comfortable in our exponential settings. Okay, let's jump into some work. So what you see on the screen then is going to be our first application, and this is going to just be kind of a nice walkthrough for us to be able to see a number of different things we can do in an exponential relationship. So pause the video, give everything a read. Okay, we're back. So what I'm going to do is I'm just going to kind of try to break this up into like 4 areas. And it doesn't mean that I'm going to be beholden to this because I'll just erase whatever I need. But maybe I'm going to try to work my way through a little bit what we're dealing with up in A, B, and so on and so on. So what we're going to begin with then, and I'm just going to get rid of, is let's tackle the first problem. Now, you sit down and you see a problem like this put in front of you. A colony of 500 bees doubles its population every 12 days, and you have to figure out how to work with this relationship. So the first thing that I want our eyes going to is the word doubles. Because we know that doubles means multiplying by 2, and if we're multiplying by 2 repeatedly, that word right there is what makes this an exponential relationship. And if it's exponential, then when we jump in and we play around with A, I know that that relationship that we just spoke about applies. Okay, I'm going to put the blinders on and I'm going to treat this like a formula. And I'm just going to plug stuff in and see what I can use the formula for. Okay, so the first thing I see is that a colony of 500 bees. That means that my initial population is 500. That's my starting value. It doubles, so when I answer the question, how is the population changing? It is doubling. That makes my G2. It doubles its population every 12 days. So up in the original problem, I know that my period must be 12. Remember, your period is the answer to the question, how long does it take to G? So how long does it take to double? That would be 12. Now, question A says, how many bees will there be in 6 weeks? That means that I am subbing in a t value. What I have to be conscious of is that if I did this, I'm missing a key part to this problem. When I plugged in that 12 was in the units of days. So that defines my exponent to be in days. So as soon as I then subbed in weeks above, my exponent isn't consistent in its units. So I have to be consistent and either change 12 days into weeks or change 6 weeks into days. And I would hope that we would find changing 6 weeks into days easier. So I had my period of 12 and I can sub in 42 for my number of days. What does that leave me with? Well, that leaves me with solving for A. And now maybe I take a look back at the problem. The problem asked how many bees, that would be me solving, for my accumulated amount, the amount the population changes to, I'm solving for the same thing. Now, this does become a bit of an exercise in button pushing. So you do not have to show me any other work other than to go to your final answer. And so what we need to do is we need to push some buttons. So when we enter that in, let's follow BEDMAS as we do it. It'll eliminate any keying mistakes. So we can deal with 2 to an exponent and make sure in that exponent, so maybe we have to put some brackets down, that our entire exponent is 42 divided by 12. That's going to get you a really ugly decimal on your screen. Immediately multiply that by 500, and that's going to get you your best approximate. Now, what I would like everyone to do is let's just write down what that approximate value is. So we would get 5,656, and I'm just going to write it down to one decimal place, 0.9. Now, I need to talk about that red line because that red line can never exist. We're trying to determine how many B's there are, and you can't have 0.9 of a B. And so then the common answer would then say, well, then let's round to 5,657 B's, and we would be incorrect. What we have to be very, very careful of here is knowing what's happening with the population and therefore rounding accordingly. If we all acknowledge that you can't have 0.9 of a B, you either have a B or you don't have a B, then we need to round this correctly. So I'm going to get rid of that purple line that we can't give as our answer and explain why. Notice that our growth is causing the population of bees to increase. And so as we increase, at some point, we then get to 5,656 bees. Our time period has made us increase just a little bit more to get the extra 0.9 of a bee. But here's the problem. If I can only have a whole bee or not a bee, then I can't increase by 0.9. That is, the 5,657th bee doesn't exist yet. And so even though that decimal is really, really big, and if you were to follow your normal rounding rules, you say, well, I have a decimal point that's 5 or greater, so therefore I round up, we would actually be incorrect in this problem. We have to round this down because that 57th bee would not exist. Okay, that's going to give us some stuff to consider as we round. However, when we work our way through some things, don't put in your mind, oh, okay, so we always round down in this problem. No. Let's follow our way through and see what else we can come up with. So I'm just going to put a little wavy line through here, and we're going to put down problem B below. Okay, let's tackle B. How many B's were there 5 days ago? Well, if I was to tackle B as if A didn't exist, then I would say I see the word doubles, and so I know that that exponential relationship applies. Okay, the question said how many B's, so I'm solving for A. That means that I started with a population of 500, and now my growth is doubling. It takes 12 days to double. How do I deal with 5 days ago? Well, I know that we spend an awful lot of time talking about how time can't be negative. But when we're talking about the continuum of this population growth, what we could do is we could say that we were dealing with 5 days prior, and therefore use a -5 as our elapsed time. Okay, we can push some buttons on that. So let's go ahead and do the same thing. So we take a look at the decimal, and our decimal is going to be about, so 2 to the exponent, -5 divided by 12. And now multiply that by our 500, and we get approximately 374.6 Bs. Okay, here becomes our rounding issue. We clearly know that we can't have 0.6 of a B. And we may be tempted to say, oh, I know from the previous problem, you round down. And so therefore, our answer would have been 374 Bs. We would be incorrect again. So let's get rid of that. Let's notice what is happening to the population when we go backwards in time. You'll notice that your population is decreasing. So again, our population decreased and got us to 374 Bs. And then a little bit extra time went by, which caused us to drop another 0.4 of a B. Sorry, I need to correct that answer for a second. We would have 375 Bs. And then we lose the other 0.4 of a B to get to 374.6. But if we acknowledge that I either have a B or I don't have a B, then I can never lose 0.4 of a B. And so therefore, my actual answer is 375 Bs. Now, I want to be clear, in terms of solutions, you would never have to show me the incorrectly rounded line. You could show me that green in the first solution and you are perfect. And for that same reasoning, if you showed me simply those lines, and I'm just going to condense that a little bit, I don't even need the therefore statement, equals 375 Bs, mark it as an approximate to show that you rounded, you are perfect. Now, what I would also like to do, though, is I'd like to tackle B from a different perspective. So I'm going to put down a bit of an or here, because we could tackle this a different way. We recognize that it's exponential, and so that yellow formula or relationship applies. But maybe we dealt with it a different way. Maybe we are still focusing on the population increasing. And so instead, you would say, well, my population is going to grow to 500. What population would I have had to start with if I was doubling every 12 days and 5 days passed? Notice now I would be trying to go backwards in time and find the original population that would allow it to grow to 500. Well, for us to be able to solve that, I need to get P all by itself, which means that I need to divide out my 2 to the exponent 5/12. You could now take that and go straight to your final answer, and you'll notice we get down to the same thing, and we're good. Mark our approximate, put on our units, we're good. Okay, let's jump into problem C. C states, how long will it take for the population to reach, or that should say to reach 16,000? Well, I notice that my population is doubling, and so I know that that exponential relationship is going to apply. Okay, what were my particulars about the relationship? Well, it says I have to reach a population of 16,000. So my population is going to grow to 16,000. It's going to start at 500. It is going to double every 12 days. How long will it take? I get a little confirmation that the only variable left over would be t, and that's what the question is asking me to find. Now, notice what you have sitting in front of you. Where is your variable? It's up in the exponent. That means we need to solve for it. So we need to get it out. And how do you get a variable out of the exponent? You get a power equal to a power base the same. So the first thing we need to do, let's get that power all by itself. So let's divide out our 500. When we divide out our 500, we're going to get 32. Well, the base of my power is 2, so I want to write 32 as a power base 2, and I know that one off by heart. Now that I have a power equal to a power base the same, I know that my exponents must be equal, and therefore multiply out your 12, you've got your 60. It's an exact answer, so I'm not marking it as an approximate. Put on your units, and we're good. So notice, in that instance, we had to actually solve an exponential equation. Our variable was up in the exponent. Okay, let's play around with D. I think everybody should be good to get D started. Pause the video now, give it a shot. Okay, we're back. So I noticed that the population is doubling, so that relationship is always going to apply. Okay, now I go through and I say, well, my population needs to reach 50,000. It started with 500. It doubles every 12 days. How long does it take? I take a look and I want to get that power all by itself, so I'm going to divide out my 500. That's going to get me 100. But now when I get to that point, I say, oh, well, it's not that easy to write 100 as a power base 2. If I can't write 100 as a power base 2, then this is where we use that property where we can use logs to solve. As a reminder, what that would state then is that my exponent equals the log of the result divided by the log of the base. Now to finish off the problem, I just have to get t all by itself, which means that I can multiply out the 12, and there is my exact answer. So now when I go through and I actually calculate that, I'm going to take my 12 log 100 and I'm going to divide that by log 2. Make sure that we get our keying sequence down. So for a little bit of help, we're going to get down to 79.7, and I'm just going to write down 26 as our answer. Now, when we're solving for time in this case, a number of days, there is no particular rounding rules about days. And so if there aren't any particular rounding rules, then we generally round to 2 decimal places. So you ask then, why did I round to the third? Well, when the population says, how long will it take for it to reach that amount? What that really is stating is we need to get to that amount. We can't come up short. And so in this instance, if I was to ever round down, then I would fall just a little bit short of 50,000. And so I need to make sure that I round this up to ensure that we at least reach that threshold, that we meet it and we get to that 50,000 number. So similar to before, you'd never have to show me that. Just come in on that rounded figure that's been rounded properly, put on your units, we're solving for days, and we're good. Okay, what we just did is we just went through 4 applications where you could solve for a number of things within the problem. A number of things. We went through in the first one, that is in A, and we went and we found and solved for an accumulated amount. In B, we solved for an accumulated amount, or we saw another way where we could solve for our initial population. In C, we worked our way through and solved for time, that being able to get a power equal to a power base the same. And in D, we went through and we solved for time, but in a manner where we couldn't get that to be a power equal to a power base the same. So we've got a lot of things that we can work with. What we want to do now is just spend some time going through a couple more applications to make sure we can knock out some of the little considerations as we work through. Okay, let's give them a shot. So let's give problem 2 a read. So let's pause the video now. Okay, and we should be back. So, a couple things that I want to make sure that we clarify about that relationship, and then, as I said, some things to consider. That when we take a look at this problem, we should be able to recognize that that is exponential right off the bat, because the population is changing by a percentage each year. As soon as I see that it's a percentage change, then I know that A equals P times G to the T over P, that relationship is true. The value of something, or the amount of something, is equal to its starting amount times how it's changing. Okay, it's that basic. However, the how it's changing has a bunch of things in it. That when we go through, we're talking about how it's growing, how long it takes, or how much time has passed, and how long it takes to do it. All those little things. Here's one of the things that we have to make sure we're good with. That what this relationship determines is what the population is. And I can't stress that enough. It doesn't calculate what of the population has disappeared. So, a very common mistake would be to start off this problem. A photocopier which originally cost $5,000 depreciates at 0.25% per year. I could, up in my exponent, write a over 1 if I wanted to, because my 1 would be how long it takes to do the 0.25. When will the photocopier, there we go, have a value less than 100? And so I'm going to find out when it equals 100 and solve. There is a big mistake in this problem, and I've written it in red. That I hope that we can look back on this problem and we can see the word depreciate. And notice that what we talk about when we say depreciate is losing value. So what that problem says is that it loses 25% of its value every year. Then that is not my G value. This relationship represents what the population is, not what it is not. And so I have to make a calculation then that says if I'm going to lose 25% per year, then therefore my growth is actually 75%. That doesn't mean that I am increasing by 75%, but that my population will be 75% of what it was the previous year. Off on the side, I'm just going to note, remember, 75% is your 3/4. And so if every year I'm multiplying by 3/4, my population is decreasing. So the most common mistake, and it's not even close in this context, is to have an incorrect G value. If I'm losing 25%, then my growth is 75%. Now, I'm just going to clean up my exponent because we don't have to write the over 1. In fact, I'd be writing boo on your page if you did. There we go. So I want to make sure that we're good just in terms of context, that we have a couple things in our background. Really what your G is a 1 plus or minus that change. And some people like to use that at times. What I mean by that is you'll notice that to come up with our G in this instance, we could have said that it was 1 minus 0.25, and therefore our G comes in on the 0.75. I want to give an alternate case. I want you to imagine that in this problem, I said that we had a photocopier that was appreciating in value. It was going up in value. And it increased in value by 5% per year. Well, then my G is going to be 1.05. Just notice that if it had been 0.05, that's going to make my population decrease. But secondly, I would hope that we would come back to like how you would calculate taxes or an after-tax price on something. If you ever wanted to calculate taxes, I would hope that not calculate taxes, calculate the after-tax price. I would hope that we would just take our price and multiply it by 1.13. You're using the exact same concept here. You're saying it is 100% of what it was before and 13% extra in tax. Notice you would have the same thing with your G. It is 100% of the value it was before, and now an additional 5%. So we're going to see that in your practice. We should be good. I'm going to get rid of all of that stuff, and we can go through and we can solve this problem. So there's your setup. The rest is simply solving. We notice where our variable is. It's up in the exponent. We got to get it out, so let's divide out that 5,000. If we divide out our 100, then we're going to get 1/50th is equal to 0.75t. I would strongly recommend leaving that as a fraction on the left side. If it's a fraction that the only way it can be turned into a decimal is by using an approximate, you're going to be wrong. Do not round off here. In this instance, it works out to be an exact value, so there is no problem with you going and taking your 1/50th and changing that to 0.02 because it's exact. There's nothing wrong with that. But I would get into the practice of using that fraction. So we get to that point. It's pretty difficult to change 1/50th into a power base 0.75, so I'm going to use my logs. So I know that my exponent is going to equal log of the result divided by log of the base. And now we're pushing buttons on that, and we should be good. Now, here's where I wanted to come back, and I wanted to address this less than word. Because notice that what we have in our equation is when we're equal to 100. The problem said, when do we get to less than 100? And here's how we can incorporate that. When I calculate that t approximate value, and I just need to go ahead and put this in red, that what I've really come up with then is approximately 13.598. Now, if I was to round that down in any way, then I would come up with a value that was greater than $100. I haven't allowed enough time to pass to reach and then get below $100. So when I incorporate that less word in this context, all that means is I have to round my answer up. And so in this instance, there's no rounding rules when it comes to us dealing with years, so I'm going to round to 2 decimal places. But in rounding to 2 decimal places, I'm actually going to round to 1, and therefore, if I round it to 13.6 years, I will have gotten below the $100 value. Okay, so we've learned a little bit about depreciating. We've learned a little bit about affecting the value of G and making sure that we have the proper value. We've also dealt with when problems use terms like less than or more than and how we can incorporate that. Let's keep it going with another example. So let's take a look at the example in 3, because we're going to introduce a topic, a concept, I should say, that when you read that problem in number 3, what this problem pertains to is something called half-life. So that's the focus of this example or this application. So I want you to pause the video, give it a read. Okay, so when you read this problem, this one might not jump out to you as exponential because you don't see anything explicit in the problem that says the population was doubling, tripling, or it was increasing, decreasing at a percentage. But what half-life actually describes is how long something takes to get to half of its value. So I'm going to take the particulars in this problem and I'm just going to draw out a timeline. It says that how much caffeine would remain in the child's body if the child ate a chocolate bar with 20 milligrams of caffeine in it. So if I said that this was like time equals 0, and at that time, let's say our amount was 20 milligrams, then what half-life says is how long does it take to get to half? So in this time period, since the half-life is described as 2.5 hours, then after 2.5 hours, our population would drop to half. Then after another 2.5 hours, it would drop to half. Then after another 2.5 hours, it would drop to half. And we could continue on and on and on with that. That is what half-life represents, and I'm hoping that you can see that this is exponential growth then. If we are cutting something in half, in half, in half, in half, over and over, then that is multiplying by 1/2 over and over and over, and there is our repeated multiplication. So in this instance then, if we recognize that half-life is exponential growth, then we can apply that relationship. Now, one of the starting points for a lot of people is that once they start to see half-life, almost like an instinct kicks in that says that they're going to make their G 1/2. And that's not a bad instinct. Like, what I mean by that is, in most cases, that's really going to help you out. You'll always be able to work your way through a problem dealing with it. It just sometimes might not be the most efficient. But as a starting point, I think that's definitely a good first step. Okay, let's put in the particulars of the problem then. It says that the half-life is 2.5 hours, and so the 2.5 would then represent our period. How long does it take to get to half? The question says, how much caffeine would remain in a child's body if the child ate a chocolate bar 20 milligrams, so that is our starting population, 8 hours before. Now, one of the key things is sometimes when we read that problem, we see the word before and we start to go, oh, so we're going backwards in time again. And we're not really. If you look at the timeline, what that would mean is at time equals 0 is when the child eats it. What we're looking for then would be 8 hours later. So our time would actually be a positive 8 in this instance, and we would be solving for our amount. There you go. So we can go ahead and we can push buttons exactly as that states. Just watch out for your keying sequence dealing with that base 1/2. There's no inherent rounding rules when we talk about milligrams, so we can round to 2 decimal places, and we should come up with approximately 2.18. So there's an introduction to what half-life represents and the way it fits into our exponential growth and decay. Okay, we're going to keep it going with another. Now you take a look at problem 4, and I want you to pause it and just give it a read. Okay, we should be back. And so one of the direct applications that we can deal with is one where we address the idea of compound interest. So when we talk about compound interest, this is a direct application for us of exponential growth or decay. That as we work our way through compound interest, what that means is that interest is earned on an investment. And what your, let's say, bank account would be a starting amount, and then you earn interest over time. But that interest gets added into that starting amount, and over the next period of time, you earn interest on your interest. And that's where that term compounding comes into play. That your interest is going to get compounded on top of itself over time. Now, our compound interest relationship is an example of exponential growth, and you can kind of see it just on the fact that we're going to be increasing at a percentage amount each year. Now, you may see the where per year. Hopefully we can see the annum and recognize that all that means is year. So, if we were to go through and then address this, we could go right back to our generic exponential relationship, and we can plug in all the details. I'm going to leave this whole solution in yellow. So we would have a starting amount of $1,000. It is growing by earning 9% per year. Therefore, our growth would be everything it was before plus the additional 9%, so 1.09. How many compounds? Well, we're getting 9% per year compounded annually, and 5 years is going to pass. And so when we get to that, you guys could go ahead and push buttons on it. I just want to put in one other detail, that we may have the over 1 in our exponent because we see that it is compounded annually. That is, how long does it take to earn 9%? So we push buttons on that, and we should come down to an approximate. We're talking about money, and so that means that we're going to round off to 2 decimal places. And so we should get about $1,538.62. Put on your dollar sign and you're good. Now, because compound interest is such a specific and often used application for exponential growth, there actually is a more formulaic relationship for it. That is, there's a specific formula that applies for compound interest. And so I think it might be beneficial for us to just take a look at that relationship for a second, because if you're pretty decent at remembering formulas, you might really like to have this one at your disposal. What we end up having is that same relationship, and it's going to look awful lot the same as we work our way through, but we're going to change a couple things. You notice that you had to remember that when we increased by 9%, that your growth was 1.09. And so the compound interest formula actually makes that explicit. It's going to put in a 1 plus into the formula. The next part that we end up getting is something that's called I. And in financial math, when you see an I, that actually means something very specific. So you'll notice in the question that we were given interest rate. And interest rates in most mathematical formulas actually go by a lowercase r. What does the I represent then? Well, that I represents what we call the adjusted interest rate. And what we mean when we say the adjusted interest rate is the way that an interest rate is adjusted per compound period. We'll see that in practice as we go. The next part for us is, since we don't really have a time that gets elapsed, financially in math, what we talk about then is, well, how many times are you going to earn that compound interest? That the exponent simply becomes what's referred to as n. And what that represents is the number of compounds. So, what I want to do is just quickly go through this problem so we can see the way it directly applies to the problem we just dealt with. So, what we could have done then is we could have said that I am solving for my accumulated amount. I have 1,000 as my initial amount. I am earning 9% compounded annually. Well, since this per annum matches up with annually, then I do not have to adjust my interest rate. So my I is 0.09. Now, how many compounds are going to take place? Well, 5 years are going by, and it's compounded annually, once per year. And so my total number of compounds would be 5. And you notice you could go through and you can just push buttons and we'll get down to that same thing. Now, if you like that formula, or if you're looking at it and saying, I don't see the point, our yellow relationship worked totally fine, I want to just maybe show you where some of the details come in as compounding becomes a little more complex. So what I'm going to do is I'm just going to erase all the little notes that we made within the problem. And what I want to do is actually change the problem. So I'm going to change some of the particulars in the problem. And one particular instance, as opposed to if invested at 9% per annum compounded annually, if I was to change that, and instead of us being compounded annually, I said that we were compounded monthly. Now, how does that play out in the problem? Well, I could start off with my compound interest relationship. A equals P times 1 plus I all to the n. And now we can plug in the details to that new problem. So I'm looking for the accumulated amount. My initial amount was still 1,000. I have my 1 plus, and now I need to adjust my interest rate. So when that problem says that my interest rate is compounded per annum, then that means that I earn, not per annum. When my interest rate is listed as 9% per annum, what that means is that I earn 9% per year. However, when it's compounded monthly, then that tells me that I'm going to receive that interest payment more often. And so my interest rate then would be my 9% per year, but now for me to adjust it, my adjusted interest rate means I have to divide it by how I'm compounded. So since I'm compounding it monthly, then I need to divide by the 12 months in a year. There's the first adjustment. The second thing now is I need to consider my number of compounds. And so as I go through, I am going to earn that interest monthly. And I need to know after 5 years. So if I'm going to earn 12 payments and 5 years are going to pass, then my exponent becomes the 5 years and 12 times per year. And so we can clean that up pretty quickly then and just say, well, 5 times 12, there is my 60. And so if we were to go through and we were to push all of that following BEDMAS, so take your 0.09 divided by 12, add on your 1, now put that to the exponent 60, and then multiply by 1,000, we're going to get about $1,565.68. So that's how we can use that direct compound interest formula to be able to get there a little easier. It still is our yellow formula. It just has some more details into it so that we don't have to consider so much adjustment when we work with it. The other part, small little note, notice that by compounding more often, everything else remained the same, but by compounding more often, you earn more interest. Okay, one more problem to work our way through. I want to go through this last one pretty quickly, so let's pause the video, give it a read, and we should be good. Okay, as we're back. So for us to kind of go through this beginning one, I think that this would be a pretty common approach. A bacterium divides into 2 bacteria every 5 days. So as soon as we see that something is splitting into 2 repeatedly, then we can see that we have an exponential relationship. Now, we have to be very careful that when we say it divides into 2, that we don't think that our g is 1/2. If something divides into 2, then 1 becomes 2, 2 becomes 4, 4 becomes 8, and so on and so on. That really what that means is my g value is 2. Okay, the rest of the problem says, initially there are 15 bacteria. What is the approximate growth rate per day? It tells me it divides into 2 every 5. So when I answer the question, how long does it take to double? That's what gives me my period of 5. What is the approximate growth rate per day? So that means per 1 day. That means my elapsed time is 1. Well, then we could go through and we could push some buttons. So when we do that, I'm just going to write this down for a little more detail. We would get approximately 17.23 bacteria. Now, I just want to stop for a second. I'm not concerned about rounding whatsoever. But I do want you to just notice that that is not the solution to your problem. The question asked, what was the approximate growth rate per day? And so what you would then have done is say like, well, this is how many bacteria I have at the end of that 1 day. 15 was the number of bacteria I had at the start. And so I would then have to take my 17.23 divided by 15, and that's what's going to bring me in on my growth rate. So you have the means to be able to go through and calculate that. And again, this is going to be a little rounded because I rounded up here and now I'm rounding again. But that would get me to approximately 1.148 and then a big thing like 7, or I can say 6 repeated would be my growth rate. Now, that would end up being a percentage. So when we go through and we think about that percentage, what that means then is there is my growth. This is by how much? So the same way earlier that we had a 9% growth rate, that turned into 1.09. There is what tells us we grow. This is what tells us by how much. Then really, this whole thing is not a percentage. That is the decimal form of a percentage. And so I need to take that last portion off, and I would then be able to say, okay, so therefore, at about 14.9%. Now, that was an awful lot of work for us to be able to go through and deal with that solution. What I want to do is I want to show you maybe a faster way. So, if I was to go through and solve this problem, there's actually a component of my growth formula that actually gives me growth, specifically growth, and I can use to calculate a growth rate, and that is my G. Now, we need to be clear, though, it's not just the G. It's actually the G with the exponent. It's our entire power. That is generic right now. But for me to turn that into something very specific, what I would be looking for is this. Now, I need to be very clear that what that represents is a growth rate. Notice that I've put a 1 in for my elapsed time. So that's what's going to tell me it's my per 1 unit. So whatever units that I put my P in for would define my growth rate per unit. And so all I needed to calculate in this problem then was to say that my population is doubling. It takes 5 days to do it. What is that growth in 1 day? And so if I was to go through then and simply calculate 2 to the exponent of 1/5, that's all I'm looking for, 2 to that exponent. Then we can push buttons on that, and you're going to end up getting an approximate, and your 1.14869, blah, blah, blah. Now, you'll notice that that is a little off. Remember that rounding that we did up here? That's why. So this is going to get me a more exact answer to that problem. I am then good that I do not need to use that 1. That 1 is what confirms to me growth. Really, what I need in terms of my rate is that rest of that decimal. And so therefore, if I was to turn that into 1 decimal place, I get down to my 14.9%. There we go. So I think we've introduced a ton of new material today. We talked about the exponential growth relationship. We showed how to use that relationship. And then we addressed a few problems that'll bring up some things that we need to make sure we can consider and some common mistakes that we got to look out for. Okay, your job. Jump in and get a bunch of practice with this stuff. Good luck.